All right, let's take a look at 2.8. What is the energy in kilojoules per mole associated with the following wavelengths? This is really a straightforward use of your two fundamental your two fundamental equations that you've learned when it comes to electromagnetic radiation, with a cutesy finishing step at the end. So we're wanting energy, and we know to get from to energy from wavelength, we go through frequency. So our first step is to use our speed of light equation, solve for our frequency, and then we use Planck's formula to solve for our energy. All right. So let's do our first step right here. Speed of light, 2.998. It's supposed to be an 8 times 10 to the 8 meters per second equals 1.82 times 10 to the negative 6 meters times frequency. Frequency equals 2.998 times 10 to the 8 meters per second. 1.82 times 10 to the negative 6 meters equals 2.998. 8 divided by 1.82 exponent negative 6 equals 1.65 times 10 to the 14th hertz. Then we're going to take that frequency and we're going to go to our next step and use Planck's formula. Now, normally, most of the problems we're dealing with Planck's formula for the energy of one photon. So we reduce the formula to E equals H times frequency. However, remember in lecture, I gave you an alternate form of that formula. E equals N times Planck's constant times frequency. So what is N? N is the number of photons. Well, if we're wanting energy in kilojoules per mole, how many photons do you think we have? Well, we have 6.022 times 10 to the 23rd. Planck's constant, then we dub in our formula, then we dub in our frequency that we solved for in the other problem, that 1.65 times 10 to the 14th hertz. And that gives us gives you 65,728 joules per mole. Well, now you just have to get to kilojoules, 1,000 joules, 1 kilojoule. So that gives you 65.7 kilojoules after you do your sig figs, because we only had 3 sig figs here, right? Because of our starting wavelength. So it would be 65.7 kilojoules per mole. That's it. Beep.